Here.
See. Let's see. I have a. I can't find it now, but let's see. I've got a list of all of the people that I have contributed so much to partial randomness before, and I don't want to leave anybody out. Let's see. Let's see here. All right, now I've got it. All right. So I'm very happy to be here at last to attend a CCR meeting. This is the first one I've ever attended. This is a wonderful meeting. Thank you to all the organizers, Elvira and Wolfgang, and anybody else who's contributed. I was supposed to be there at Notre Dame, and I'm sorry for not canceling at the last minute just because of a little illness, and similarly for Cape Town, I was supposed to be there and didn't show up due to just minor. I just got a cold or something the week before, so I wasn't fit to travel. That's all. Anyway, it's great to be here, and I've gotten. I'm somewhat of a latecomer to this area of randomness, but I've now published a few papers in it, and especially it's tied into degrees of unsolvability in my mind. I'll explain a little about that later in the talk. Probably unnecessary for this audience, but I'm going to just mention the definition of randomness. This is just mostly for notation. So this is Martin-Love randomness for a point in the Cantor space. We'll only deal with the Cantor space. We work with the Cantor space, 0, 1 to the n. N is a set of positive integers or natural numbers. So a point in the Cantor space is an infinite sequence of zeros and ones. Those are the points in the Cantor space. Let mu be the fair coin probability measure on the Cantor space. So each point is viewed as this measure is such that each point is viewed as the outcome of an infinite sequence of tosses of a coin, fair coin, heads or tails. So now consider subsets of the Cantor space which are effectively null, that is effectively a measure 0, and then down here below I'm defining exactly what that means, but somehow it's a set of measures 0 which can be described by a computer. And a point in the Cantor space is then defined to be random if it belongs to no effectively null set. It doesn't belong to any effectively null set, so it doesn't have any property that is only shared by a set of things of measure 0. Any easily describable property, at least. So this is Martin-Love's 1966 definition. So the details of the definition, and I'm giving this just for notation because later I'm going to generalize this to partial randomness. So for each finite sequence of, so 0, 1 star is the set of finite sequences of zeros and ones. For each finite sequence of zeros and ones called tau, we'll write a square bracket tau is the set of points in the Cantor space such that tau is an initial segment of that point. So it's an initial, it's a finite sequence of zeros and ones that is an initial segment of the infinite sequence of zeros and ones, x. Okay, so the measure of square bracket tau then, that's what's called a cylinder set. So the measure of tau is, square bracket tau is 2 to the minus absolute value of tau. Absolute value of tau means the length of tau. Now, let's see. If A is a set of finite sequences of zeros and ones, we'll write square bracket A as the union of square bracket tau for tau belonging to A. And then a set is said to be effectively null if it is included in the intersection of square bracket AN, where the measure of square bracket AN is less than or equal 2 to the minus n, or 1 over 2 to the n, and the ANs are uniformly recursively enumerable, and I'll use this abbreviation URE. So a sequence of sets of binary strings is said to be URE, or uniformly recursively enumerable, if the set of pairs tau comma n such that tau belongs to AN is a recursively enumerable set. Okay, so that's the definition of Martin-Love randomness in complete detail. Now, so what we're going to do with partial randomness is instead of talking about the measure of square bracket AN, we're going to talk about some other way of assigning a weight to AN. In other words, we'll talk about, in other words, the basic idea of Martin-Love tests will be the same, but we will assign a real number to a set of binary strings, and it won't be exactly the same as the measure of square bracket A. It'll be instead some weight, the weight of A in some sense, which will vary from situation to situation. All right. Now, but I also want to comment on how Martin-Love randomness is related to prefix-free Kolmogorov complexity. And again, for this audience, I'm sure I don't need to review this definition. Actually, let me go through this pretty quickly because I won't really refer to it. Anyway, to give the definition of prefix-free Kolmogorov complexity, we'll consider partial recursive functions from the set of finite binary strings to finite binary strings. Let phi be such a function. We say that phi is prefix-free if the domain of phi is prefix-free, which means that there is no pair of strings in the domain such that one is a proper initial segment of the other. Then you let a k, and I'm going to use the notation kp for prefix-free Kolmogorov complexity. Kp sub phi of tau is the minimum sigma, the minimum length of a string such that phi of sigma equals tau. And then we can construct a phi which is universal in the sense that kp sub phi of tau is less than or equal kp sub c of tau for any other partial recursive function modulo a constant c for all tau. And c is constant independent of tau. So the prefix-free, once you know that there exists a universal partial recursive function, you define the prefix-free complexity of tau as the kp phi for where phi is the universal prefix-free partial recursive function. And so kp is well defined up to plus or minus a constant. That's obvious from the definition. And by well-defined, I mean that kp is independent of the choice of the universal prefix-free partial recursive function. Of course, it's not actually independent. It's only independent up to plus or minus a constant, which is why when you're dealing with Kolmogorov complexity, it seems to me as a newcomer to the field, you're dealing with asymptotics. You're not really dealing with the inherent complexity of a specific string, but you're dealing asymptotically with the complexity of arbitrarily long strings. Okay, so roughly speaking, the idea is that kp of tau, the prefix-free complexity of tau, is the number of bits of information needed to describe tau. Now, in particular, you can prove that kp of tau is less than or equal to the length of tau plus a small annoying factor, 2 log base 2 of the length of tau plus a constant. It's not, the essential part is this, that the complexity of tau is less than or equal to the number of bits of tau, because you can describe tau by simply writing out the bits of tau. Just for technical reasons, there's these annoying extra terms in the inequality. We'll see later that there's another kind of complexity called a priori complexity where that goes away, which is somewhat better behaved than Kp. All right, now the theorem relating Martin-Löf randomness and Kolmogorov complexity is Schnorr's theorem, or I've heard this also called the Schnorr-Levin theorem. Let x restricted to n, so again, x is a point in the Cantor space. X restricted to n denotes the initial segment of x of length n. So x is an infinite sequence of zeros and ones. X restricted to n is the sequence of length n, which is the initial segment of length n of that sequence. So Schnorr's theorem says a point in the Cantor space is Martin-Löf random if and only if the complexity of the first n bits of x is greater than or equal n modulo a constant. All right, so that's a basic theorem which I'm going to generalize to partial randomness or discuss the generalizations. Now there are two recent books on randomness and Kolmogorov complexity, the book by Andre Nice, which I think I saw a copy of out on the desk out there, and there's a book by Rod Downey and Dennis Hirschfeld. These are wonderful books that have a huge amount of information. I've been consulting them frequently ever since they were published. Okay, now we get to partial randomness. So I'm going to state this partial randomness idea. Partial randomness has been discussed a lot in the literature already. I'm going to state this in a very general way. Fix a computable or recursive function from binary strings to the real numbers. Actually, the extended real number system. It doesn't matter. You can just think of it as a function from finite sequences of zeros and ones to the natural numbers. But the domain is the set of finite sequences of zeros and ones. So then we'll define the f weight. So if A is a set of strings now, instead of the measure of square bracket A, we will talk about the f weight of A. The f weight of A is this expression here, the sum for all tau in A of to the minus f of tau. So we'll just call that the weight with respect to the function f. F is the only restriction on f that I'm placing is it's a computable function. It actually doesn't even have to be computable. I mean, this definition makes sense. All right. Now a point is said to be f random. Now here I think it doesn't make much sense if f is not computable. A point x is said to be f random if it's just like the definition of Martin-Löf random. X does not belong to the intersection of square bracket an for all uniformly recursively enumerable sequences of sets an such that the f weight of an is less than or equal to the minus n. So instead of the measure of square bracket an, we're looking at the f weight of the set of strings a sub n. All right, so that's how we define f randomness. So it's a very Martin-Löf-like definition. It's just a generalization of the usual definition of Martin-Löf randomness. Now a special case is Martin-Löf randomness, because if you let f of tau be the length of tau, x is Martin-Löf random if and only if it is f random for that function, or you could call it length random. So that's a special case. Now, if s is a rational number, let's say that x is, here's another special case. Let's say that x is s random. S is a rational number like a half. We'll say that x is s random if x is fs random, where fs of tau is s times the length of tau. And then the effective Hausdorff, so for instance, well, I'll get back to this, but you're half random if you're random with respect to the function f of tau equals, if you're f random where f is the function, f of tau equals half the length of tau, for example. So now the effective Hausdorff dimension of x is defined, or can be defined as the supremum of all s such that x is s random. So the bigger s gets, the less likely x is to be s random, and there's a threshold where it stops being s random as x gets bigger, and the effective dimension is that threshold. So fundamental results concerning S randomness and effective Hausdorff dimension have been obtained by many researchers, including Tadaki, Riemann, Tervain, Miller. Tadaki is here, actually. I thought I caught a glimpse of him. Oh, there he is. Okay. Yesterday. Oh, good. Okay. Yeah, but I don't know where those other guys are. Anyway, they've probably been at too many CCR conferences already. Okay. All right. Yeah, let me see. I want to, I guess I should, at some suitable point. Well, anyway, here's the generalization of Schnorr's theorem, replacing Martin-Löf randomness by F randomness. For any recursive function, any computable function f, a point in the Cantor space is f random if and only if f provides a lower bound on the prefix-free complexity of the first n bits of n. So it's the complexity of x of the first n bits of n is greater than or equal f of the first n bits of n modulo a constant. That's the generalization of Schnorr's theorem, and that's proved very simply. Just the standard proof of Schnorr's theorem works to prove that. So, for example, x is 0.5 random or 1/2 random if and only if the first n bits of x contain at least n over 2 bits of information, modulo an additive constant. I mean, I'm speaking loosely here, measured by the prefix-free complexity of the first n bits of x. Similarly, x is square root random if and only if the first n bits of x contain at least square root of n bits of information. So these examples are intended to suggest if you vary f, if you consider f of different growth rates, f could be different slow-growing order functions like 1/2 n, 1/3 of n, the square root of n, the cube root of n, log n, log n, 1/2 log n. You get different notions of randomness by varying, different notions of partial randomness by varying f. And this is actually, to me, from the perspective of degrees of unsolvability, these classes of classes of reals that are partially random or f random for different f's are very different from each other. They have different degrees of unsolvability. The problem of finding a real which is square root of n random is has strictly greater degree of unsolvability. It's strictly harder than the problem of finding a real which is cube root of n random. This is a result actually of Huddleston, which I'll mention later. These kind of things. I mean, so you have a whole hierarchy of different kinds of randomness, f randomness, depending on what f is. All right. Now, all right. So that's yeah. Maybe this is a good time to read my list of people who have contributed to partial randomness over the years. Kaluda, Huddleston, Kjos Hansen, Merkle, Miller, that's Joe Miller, Riemann, Steiger, Tadaki, and Tervain. Those are the ones I can think of that have really, impacted my own work at least. Anyway, now in this talk I'm going to talk about propagation of randomness and propagation of F randomness. So what do I mean by propagation? This has to do with randomness relative to a Turing oracle. So, you know, I don't want to, well, I even made an attempt here to explain about Turing oracles, but I guess I basically have to assume you already understand what a Turing oracle is. So let me first, I'm going to present some results concerning propagation of F randomness. But first, and they are generalizations of known results concerning propagation of Martin-Löf randomness. Propagation, we're talking about Turing oracles, randomness relative to certain Turing oracles. So let me describe the original results for propagation of Martin-Löf randomness. So here's the thing about Turing oracles. A point y in the Cantor space, or just any real, maybe of any kind, may be used as a Turing oracle. So this means that our Turing oracles, our Turing machines, have the added capability of accessing information about y. If y is known, then the Turing machine can ask, okay, what is y of n? Is it 0 or 1? And an example is the function psi of m equals the least n such that n is greater than m, and y of n is equal to 1. That function is computable using y as a Turing oracle, because you can start with m plus 1, m plus 2, m plus 3, and ask whether whether y of those values are equal to 1 until you find a value that's equal to 1, and then that's the output. So, all right, so we say that x and y being 2 points in the Cantor space, x is Turing reducible to y if x is computable using y as a Turing oracle. So this is Turing reducibility, the usual notion of Turing degrees and Turing degrees of Turing degrees. We also say that x is random relative to y, and so randomness, the idea of randomness, can also be relativized to a Turing oracle, and Kolmogorov complexity, for that matter, can be relativized to a Turing oracle. We say that x is random relative to y if x passes every Martin-Löf test such that the measure of the nth set in the test is less than or equal to the n, and the sets are URE relative to y, that is, using y as a Turing oracle. That's the Turing machine which outputs or generates these sets is allowed to use y as a Turing oracle. Okay. So here's the theorems on propagation of randomness. These are by now classic theorems, I guess. Well, actually the Miller-Yu one was only published in 2008, but it was known, they proved it some years before that. So theorem 1, assume that x is random, that is Martin-Löf random, x is Turing reducible to y, and y is random relative to z. Then x is random relative to z. So all of these theorems are going to say if x is random, then x is random relative to z for some kinds of Turing oracle z. So in other words, if x is random relative to nothing, using no oracle, guess what? X is random relative to some serious oracle. X is more, a real that is Martin-Löf random is more random than it has a right to be. It's not only Martin-Löf random, it's Martin-Löf random relative to certain oracles. That's what all these theorems say, propagation. I'm calling that propagation. I would use the word enhancement perhaps, except I think Andre already used that word with a different, randomness enhancement or something like that. Andre already used that word with a different meaning. All right, now theorem 2, Theorem 2, assume that x is random, then x is random relative to some PA oracle. So that's a serious oracle. That's a powerful oracle. This is just referring to Martin-Löf randomness. but I'm going to generalize both theorems 1 and 2 to partial randomness or F randomness. Now, okay, so for those who are, just for terminology, a P aorical is a Turing oracle Z such that Z is powerful enough to compute some complete consistent theory extending Peano arithmetic, and that's why we call it a PA oracle. But actually, this doesn't have anything to do with PA, Peano arithmetic, because instead of Peano arithmetic, you could use ZFC or Z2 or primitive recursive arithmetic or Robinson's Q, any effectively, essentially undecidable theory. But these are powerful oracles. I mean, these are oracles that are powerful enough to solve the problem which Tarski proved was unsolvable, namely the problem of, or Tarski and Gödel, I guess, the problem of finding a complete extension of Peano arithmetic.
Yeah, just for clarification, so how is it with the number omega, right? Which is
Omega is certainly a PA degree, but it's more powerful. Omega is PA degrees are not as generally not as powerful as the halting problem. Omega is, as far as Turing degree, omega is Turing equivalent to the halting problem. It's a pretty crude.
I'm saying that, but so now this says that it is random. It's a random number. It's a random sequence.
It's random relative to some PA.
Oh, if X. Oh,
weak to compute.
yeah. Okay, I see. What if X is omega? You're asking.
You know, what is X is omega?
Yeah. Okay. If X is omega, yeah. Well, omega is random relative to some PA oracle. Yeah.
So, but oh.
There's some PA oracle which is pretty powerful, but not powerful enough to de-randomize omega.
Oh, but
PA oracle just separates provable and refutable statement. It just doesn't say what is true. So we separate them in a strange way, so it doesn't help for omega.
Right. Okay, so these are the two theorems which I'm referring to as propagation of randomness. Theorem 1 is due to Miller and Yu, a paper published in 2008 in the Transactions of the American Mathematical Society. Theorem 2 is due independently to several different groups. There's a paper by Downey, Hirschfeld, Miller, and Nice in 2005 where this theorem was proved. There's a paper by Reimann and Slayman, and they proved it about the same time, and in fact Downey, Hirschfeld, Miller, and Nice cite the fact that they proved it, but for some reason that paper hasn't been published yet. I think it's part of a larger paper on non-continuous, non-continuously random things. And then I and Yokoyama rediscovered this theorem because we just didn't know about it much later. We rediscovered it much later. Maybe it was already in the air in some sense. But I'll explain. Theorem. You might ask, what is the point of these theorems other than just enhancement of randomness or something? Well, Theorem 2 has actually, Theorem 1 I don't know that it has any big applications, but Theorem 2 about propagation to a PA degree has been very useful, or a PA oracle has been very useful in the study of randomness. So Reimann and Slayman are using it to prove that a point in the Cantor space is non-computable or non-recursive if and only if it is non-atomically random with respect to some probability measure on the Cantor space. So they characterize the points in the Cantor space that are random in a non-trivial way, non-atomically, with respect to some probability measure, and that turns out to be just the non-computable points in the Cantor space. Yokoyama and I applied this to study in the reverse mathematics of lobe measure, and Brodka, Miller, and Nice, a paper that's been submitted for publication, they applied this to prove Theorem 2 to prove that a point in the a point on the real line is random if and only if every computable continuous function of bounded variation is differentiable at x. So that's a very beautiful result that is proved using propagation of randomness, because what you have to do is you have to separate a function of bounded variation into non-decreasing and non-increasing components, and that can be done using a PA oracle. So, all right. So now, here at the bottom of the slide, theorems 3 and 4 are the generalizations of these things to F randomness. And you see theorem 3 looks exactly the same. Assume that X is strongly, okay, I'll have to define strongly F random, but it's a variant of random F randomness. Assume that X is strongly F random. Assume that X is Turing reducible to Y, and Y is random relative to Z. Then X is strongly F random relative to Z. So strong F randomness propagates. I like to call this theorem the XYZ theorem, just because it has X, Y, and Z in it. X, Y, and Z all play different roles in this theorem. It probably looks a little strange. You may have to, if you haven't seen this theorem before, you have to think what it means. But anyway, that's the theorem. And then for theorem 4, well, just forget about X sub I. Just if X is strongly F random, then X is strongly F random relative to Z for some PA oracle Z. Now, actually, this theorem 4 is more general. It says that if you have a sequence of things, xi, which are strongly fi random, they just, a sequence of things that are partially random in different senses, then you can find one PA oracle Z such that all of them are strongly fi random, or have the same exact amount of partial randomness. Okay, so those are our main theorems, theorems 3 and 4. Now, I'm going to define, but I have to define strong F randomness, because these theorems, another point I want to make is that these theorems do not hold for F randomness. They only hold for strong F randomness. So what's strong F randomness? Strong F randomness, instead of the weight of A, you use what is called the prefix-free F weight of A. Instead of the F weight, you use the prefix-free F weight. The prefix-free F weight of A is the supremum of the weights of the prefix-free subsets of A. So in general, that's smaller than the weight of A. And if you do that, then repeat the definition of marginal randomness or F randomness using prefix-free weight instead of weight, you get the notion of strong F randomness. And that's what we're using here. So for example, if X is strongly F random, then X is strongly F random relative to some PA oracle.
Was theorem 4 hold for standard marginal randomness?
Yes, it also holds for standard marginal randomness, and that seems to be new also. That seems not to have been known before. Yes. For sequences, you mean? For sequences. Yeah.
This is a consequence of theorems 1 and 2, because we can find an oracle which computes all the xi and then...
So the way you deduce theorem 4 from theorem 3 is you use the Kuchera-Gotch theorem to find a real which is random, marginal random, and computes xi for all I, and then you apply theorem 3. That's how you do this. And then you apply, theorem 2, I guess, and then you apply Kuchera-Gotch plus theorem 2 to theorem 3 plus theorem 2 plus Kuchera-Gotch easily combined to get theorem 4. Okay. All right. Now, okay, so as I said, these theorems, these propagation theorems for partial randomness, depend very much on using strong F randomness instead of F randomness. So let me talk a little about contrasting those two notions. First of all, theorems 3 and 4 fail if we replace strong F randomness by F randomness, indeed there is a 0.5 random oracle or half random X, which is not half random relative to any PA oracle. That's a fact. So, so I guess what I want to say is that strong F randomness appears to be a more stable notion than F randomness. For example, it propagates better. That's what I'm saying. These propagation theorems hold for strong F randomness, but not for F randomness. Now, just clarifying the relationship, assume that X is F random relative to some PA oracle, then X is strongly F random, and therefore strongly F random relative to some PA oracle. So strong F randomness is actually equivalent to F randomness relative to some PA oracle, but it's not equivalent to F randomness. That's a weird insight that we got while working on this paper. Okay. Finally, there is a little bit of relationship between these things. If X is G random, where G grows a little bit faster than F plus 2 log base 2F, for instance, then X is strongly F random. So being strongly F random follows if you're G random for some G which grows a little bit faster than F. And I think this was essentially already known. This follows from known things about, I said it was first proved in 2011, but theorem 7 I think was probably already really known one paper we consulted was a paper by Uspensky and Shen on different varieties of Kolmogorov complexity. I'll explain how that comes in, but I think it was already implicit there. Anyway, all of these results are in a paper that we just submitted by Higuchi, Huddleston, myself, and Keita Yokoyama. Kojiro Higuchi is here at this meeting. He's in the back there. Yokoyama couldn't be here, and Huddleston couldn't be here, but they're all co-authors. All right. Now, one thing I haven't explained, just to round things out. Strong F randomness. How does Schnorr's theorem generalize for strong F randomness? What is the Schnorr's theorem version? What form does Schnorr's theorem take on for strong F randomness? The answer is very nice. Just as F randomness can be characterized in terms of prefix-free complexity, or KP, as I called it, so strong F randomness can be characterized in terms of a slightly different complexity notion, which is known as a priori complexity, or KA. And I'm taking that notation from a paper by Uspensky and Shen. So a priori complexity is a slightly different kind of complexity. It's also Kolmogorov complexity, essentially, but it's a little bit more sophisticated in how it's defined. So here's the definition. A semi-measure is defined to be a function m from finite strings of zeros and ones to the unit interval 0, 1, with the property that m of tau is greater than or equal m of tau followed by 0 plus m of tau followed by 1 for all tau. So it's a I would like to call it a submeasure. M of tau is not is bigger than, possibly bigger than m of tau 0 plus m of tau 1. But it's called a semi-measure in the literature. And we say that m is left recursively enumerable if the real numbers m of tau are uniformly left recursively enumerable. In other words, there's a Turing machine such that if you input tau, that Turing machine will output a increasing sequence of rational numbers which converge to m of tau. So one can construct a left RE semi-measure which is universal in a certain sense. That is, it modulo a multiplicative constant, it dominates any left RE semi-measure. It's one left RE semi-measure which dominates all left RE semi-measures. Oops. So there's a universal one, and then the a priori complexity of tau is defined as minus log base 2 of m of tau. And as in the case of Kp, this is independent of the choice of a universal left RE semi-measure modulo an additive constant. Now, I can't read Levin's papers, but as I understand it, these concepts are due to Levin. Is that correct?
It's in a paper of Levin and Zvonkin,
Okay.
which is readable actually.
Really? Okay. Oh, golly.
It's written by
and
Zvonkin.
maybe one should not forget Solomon, actually introduced.
For semi-measures on trees.
But yeah, in his a priori probability, or at least, he has many versions.
Okay.
Anyway. Yeah, okay. Maybe Solomon, someday I'm going to have to read the history of this subject. Anyway. So it's a little more sophisticated. This kind of complexity is not as well known as prefix-free complexity. I notice in the books of Downey and Hirschfeld and Nice, they mostly talk about prefix-free, although in Downey and Hirschfeld they do say a lot also about a priori complexity. Anyway, Schnorr's theorem holds for strong randomness is just the same as it was before for F randomness, but using a priori complexity instead of prefix-free complexity. So using Ka instead of Kp, we get a Schnorr-like characterization of strong F randomness, and this is it. And this is for any computable function on finite strings of zeros and ones. A point x in the Cantor space is strongly F random if and only if the a priori complexity of the first n bits of x is greater than or equal f of the first n bits of x, modulo a constant. And I believe this theorem is essentially due to Kaluda, Steiger, and Tervain. I learned about it in a paper of Riemann. And Levin says, I've heard him say that Ka, a priori complexity, is better behaved than prefix-free complexity. Prefix-free complexity, I guess people generally believe that it's better behaved than plain or simple complexity. But this Ka is even better behaved. And an example of that, this is a sort of a low-level example, but Ka of the a priori complexity of tau is indeed less than or equal the number of bits in tau. As you would, it fits more with intuition about complexity, bits of information or information theory. So Ka is better, and I never understood what Levin meant by saying Ka is better behaved than Kp until recently while working on this paper, because you see. Strong F randomness, which is defined in terms of Ka, is the one that propagates nicely. F randomness doesn't. All right, now I want to relate this to degrees of unsolvability, and I want to leave time for questions too. Let's see. So let me just give you a little bit about degrees of unsolvability. So let P and Q be subsets of the Cantor space. We will say that P is so what you do is you view P and Q as problems. That is, these are called mass problems. A mass problem is a subset of the Cantor space essentially, but we view it as a problem. The problem, if P is a set in the Cantor space, we view P as a problem, the problem of finding an element of P. So to solve the problem, you don't need to know all of P. You just need to find one element of P. That's what it means to solve to solve P. To solve P means to find an element of P. And now, with that idea in mind, So P is solvable, for instance. P is just outright solvable if there's some computable element of P, if P has some computable element. In that case, P is said to be solvable as a problem. As long as there's one computable element of P, P is solvable. Now, what do we mean by saying one problem is reducible to another? Maybe both problems are unsolvable, but what do we mean by saying that one problem is reducible to the other problem? Well, what we mean is that, and this is called weak reducibility, but it's really a very natural notion of reducibility. P is reducible, weakly reducible to Q if and only if for all y in Q there exists an x belonging to P such that x is Turing reducible to y. Okay, so if you have any solution of Q, you can use that to compute a solution of P. In that case, we say P is reducible to Q. So, typically problems in real life and also in this subject, typically problems have many solutions, right? They may have no solutions, or they may have, in which case P would be the empty set. But, typical problems have many solutions. They don't just have one solution. And so what does it mean for one problem to be reducible to another? It means for any solution of the second problem, you can use that to compute a solution of the other problem. Okay, so that's due to that concept is studied by Muchnik. This is Muchnik Senior, so these are called Muchnik degrees, or just calling them degrees of unsolvability. All right, so this is the concept of degrees of unsolvability that I'm talking about. And given a computable function f of the type we've been using, there is an associated mass problem k sub f, the problem of finding some point in the Cantor space which is f random. So let little k sub f be the degree of unsolvability of k sub f. In other words, it's the equivalence class of, well, the degree of unsolvability is the equivalence class of problems under mutual reducibility. K sub f is the degree of unsolvability of the problem of finding a real which is f random. And so this is the theorem I was referring to it before, assuming some conditions on f and g, kf is strictly less than kg. Assume that g grows a little bit faster than f, and also assume that f is length invariant, that's this first condition, and what's called, I guess, monotone increasing or non-decreasing and convex. These are just some mild conditions. I mean, all the standard examples, like f of tau equals the length of tau, f of tau equals a half the length of tau, f of tau equals the square root of the length of tau. All those satisfy these conditions. Then, if g grows a little bit faster than f, then there exists a strongly f random real, in fact, such that no g random real is Turing reducible to x. In other words, k sub f is strictly less than k sub g. These are different degrees of unsolvability. So a special case of this result was proved in a celebrated paper by Joseph Miller in the case when f is f of tau equals a constant times the length of tau. But then Huddleston has generalized this to prove this theorem, and that's a paper that's been submitted for publication. So I wanted to mention that. Huddleston and I got interested in this because of the lattice E sub w. E sub w is the lattice of weak degrees or Muchnik degrees of non-empty, effectively closed sets in the Cantor space, or pi01 sets in the Cantor space. And I have a survey paper on, I've written a number of papers on this subject. E sub w, and I have a survey paper published recently in the centennial issue of the Tohoku Mathematical Journal. The lattice E sub w is a rich structure. It contains many interesting degrees of unsolvability, and I'll show you a picture of E sub w. See, it's a very interesting picture. There are a lot of black dots in there. Each black dot represents a specific degree of unsolvability that you can name. You can give a description, you can name, okay? Except one. There's one black dot in there which doesn't represent any specific degree of unsolvability. I'll let you figure out which one that is. Okay. But most of those dots, one is the degree of the problem of finding a completion of pan-arithmetic, a complete theory extending pan-arithmetic. 0 is the degree of solvable problems. R1 is the degree of the problem of finding a Martin-Löf random real. R2 is the degree of the problem of finding a two-random real. K sub f I've already described. That's the problem of finding a real which is f random. D is the problem of finding a real which is diagonally non-recursive. B alpha is the degree of the problem of finding a real with the property that the alphth Turing jump of the empty set is LR reducible to it. So all these are very standard. Thank you. Very standard degrees. By the way, I should mention I saw Alan Selman is over there telling me to be quiet. He proved an interesting theorem about weak reducibility versus strong reducibility, that for the enumeration degrees they coincide. Anyway, that's the picture. So I guess really I can stop almost right now. Why don't I stop? This is the description of the results about B sub alpha. Here's what LR reducibility is. It's equivalent to LK reducibility. And it's here's a question I don't know the answer to. I haven't thought about it too much, and I suspect I know what the answer should be, but there's a theorem of Miller, Kjos, and Solomon that LR reducibility is equivalent to LK reducibility. LR reducibility is defined in terms of prefix-free complexity. What happens if we replace prefix-free complexity by a priori complexity?
Then there is no low sets.
Oh, you know the answer.
No K A low, because just the sequence is computable if complexity is bounded.
Yeah, but it's still a reducibility, so it still could be something interesting there, I guess.
Okay, I'll discuss. I want to ask you this. So you think you know the answer to this question?
No, I'm not sure I understand the question, but okay.
Well, the question is, does this theorem still hold if we replace Kp by Ka?
I think Sasha said something like K2 would be convex.
The answer is no.
The answer is no.
Okay. All right. Thank you. All right. Good. So, all right. Well, anyway, here's another picture of the same picture, actually. And that's the end. Let me just say that this idea of degrees of unsolvability here was an outgrowth of ideas of Kolmogorov also. Kolmogorov has comes up several ways in this talk. Kolmogorov was interested in intuitionism, and he developed something called the calculus of problems as a non-rigorous explanation of intuitionism. And later, Medvedev and Muchnik, that's Muchnik Sr., proposed these strong and weak reducibilities, or strong and weak degrees, as a rigorous version of Kolmogorov's calculus of problems. So these things actually form a model of intuitionism. Okay, so I'll stop there, and these are just some of my papers. And let me stop there. Thank you.
I have a question and even kind of conjecture. So you say that the theorem about propagation of randomness for f randomness,
Yes.
and maybe it's just
strong randomness.
strong f randomness. Sorry.
Yes.
So in terms of a priori
A
compatibility.
priori, yes.
But isn't it true that you can get even a lower level thing if you have an a priori, if you have a string and you look at an oracle and you look how much this oracle decreases the a priori complexity of the string, this is bounded by the randomness deficiency of, by just the things which are finite in the theorem. Somehow, what I am saying that maybe it's possible to derive your theorem for a theorem just saying, not saying about without f. So you can separate this estimate, this bound,
Yeah.
and the argument with f, I guess.
Well, yeah, I thought about that a little bit. In other words, you're saying, maybe there's some theorem saying there is a PA oracle which almost for any strings or for a wide class of strings does not decrease the complexity too much.
It would be also good, but this is stronger than what I'm saying.
Oh, what are you saying?
I'm just saying that if you have a string and an oracle, and you see how much the oracle decreases the complexity, a priori complexity of the string,
Yes.
it can be estimated by the z, by the complexity of x given y and randomness deficiency of y given z's. But just what is finite in your theorem. But okay, if it's not clear, don't worry. But what I'm saying is that actually I think f is not very essential in the theorem. It's just because f is arbitrary.
Yes.
So it's
Yes.
more about
Yeah. I've thought that a couple times that there should be some underlying thing about strings here. That just you're saying that you can find a PA oracle, for instance, that doesn't decrease the complexity of there's a sort of limit on how much it decreases the complexity of strings. But
do you know whether you can find an oracle that decrease complexity of two strings even? Of one string it's more or less clear, but you have two different strings and you want to find an oracle which keeps them as complex as they were.
Don't know. Okay. I don't know. And I'm not really. I guess I'm not really used to. Like you said, I'm more used to thinking about infinite sequences than finite sequences.
Yeah.
Yes.
In your degrees of unsolvability picture, there was a degree A, which was just an isolated point or something. What is that?
That's any recursively enumerable Turing degree. So there's the Turing degrees are embedded in the Muchnik degrees or weak degrees, and then that degree there is the infimum of any recursively enumerable Turing degree with one. Actually, the Muchnik degrees form a lattice. Every two degrees have a supremum and an infimum, and this is the infimum of those two degrees.
Why don't we stop here and thank the speaker again?